Okay, all right. So here's the last example I want to show you all in this section. And this is an example of how using vectors it can be a really convenient way to understand parameterizations. So here's a scenario. But let's just talk through personal experience on how you can relate to this example. Y'all have probably seen bicycles riding down the road at various times. But more to the point, if you've seen a bicycle riding down the road at like dusk or nighttime or something like that, well, that reflector on the wheel, right, catches the light from the street lamps, and it's brighter than the rest of what you see. The bicyclist himself, and it's kind of dark out, so it's kind of hard to see. But that reflector is quite visible, and so you'll see that reflector kind of go like this and make this kind of zigzag pattern. Okay? So, how would you describe that curve? The curve made by the reflector. How would you describe that algebraically? And it's a pretty hard question, really, as it turns out. So this reflector, do like that as the bicycle goes along. Can you view this curve as a graph of some function? What is this the graph of? It turns out that that's a really hard question. Right? Not easy to answer that question at all. But it's a really easy, it's not that big a deal to understand that curve by parameterizing it. And so let's do that. Here's the idea. I'm gonna view that reflector as a sum of some simpler vectors. So let's think about the axle of the bicycle. The axle of the bicycle is doing something really easy. The axle is just going in a straight line at a constant speed. No problem. Okay. What else can I say about this reflector? Well, this little vector here is also pretty easy to understand. That little vector, as the bicycle moves on down the road, now keep in mind, vectors don't have locations. Vectors only have directions and magnitudes. I'm going to draw the following vectors. I'm going to draw them momentarily, just based at that same point. That little vector is just doing this. Or you might say that vector is just going around in a circle as the bicycle wheel moves along, right? And I appeal to your physical intuition. As the bicycle goes that way, the wheel turns like that, and so this purple vector goes around kind of clockwise, if you will. Yeah? Okay. All right, and then I make the following pretty believable appeal, and that is that the location of the reflector is just, it's the location of the axle, which is easy to understand, plus this difference vector, x minus a. That difference vector is easy to understand. This purple difference vector is just going to, we just have to figure out how to parameterize a circle going clockwise. So all we're going to do ultimately is we're going to parameterize the motion of this reflector by finding this blue vector as a function of its input parameter and finding that purple vector as a function of an input parameter. That's it. That's just not that much to it. So this is all written down on the other page. So let's just go back up to where that is, or do I have it down here? Okay, let's do it like this. Let's start with the axle. What is the location of the axle as a function of time? Excuse me. What's going to be our input parameter? I have a suggestion for our choice of input parameter here. Time. We could make that work, but there's an easier choice in this case. Let's think about how both of these are functions of this angle. As the bike moves along, this angle, theta, increases, right? And that's just representing how much the tire has turned, how much the wheel has turned. And it turns out that's going to be a really easy, it's going to be a very convenient choice for parameter. And then if you want to know, what's position as a function of time instead of position as a function of angle, then we have to know how fast is the bicycle moving. But that's just a conversion. It's not that big a deal. So we're going to do everything in terms of theta. Okay. Right. So, what is the position of our axle? The axle, its y-coordinate is just constant. Right? The y-coordinate is, let's see, where did I write this down? The y-coordinate is 16. Let's see, the details of this scenario. The bicycle has radius, the wheels have radius 16, and the reflector is exactly half of the way from the tire to the axle. Okay, so 16. There's going to be an 8 showing up at some point. Okay. Everybody on board so far? The axle has y-coordinate that's constant at 16. Okay. Next observation I want to make, and this is just a physicsy kind of observation. We're assuming that this is a dry road and that these are nice new tires and that there's no slipping. And so the observation I'll make is if there's no slipping, then the amount of road that has seen rubber should be the same as the amount of rubber that has seen road. Right? Otherwise it would be slipping. Okay. What that tells me is that in this scenario down here where the tire has moved a little bit, this amount of rubber that has seen road, right, that point right there was the point that was touching the road immediately, instantly. But as we've moved a little ways, more rubber has seen road. So the amount of rubber that has seen road equals the amount of road that has seen rubber.
Exchange refers to contact.
Contact. Yeah, sloppy language, but yeah, contact. Yeah, absolutely. Yeah. Okay, with that appeal, I can then tell you the x-coordinate. Right, this is the x-coordinate this is the first coordinate, I'll say, of our A vector. And it is that arc, the length of that arc. That arc has angle theta because the angle by which the wheel has turned is the angle by which the wheel is turned. I mean, these are clearly the same theta. And the length of an arc is radius times angle. Old geometry fact from way back when. So that means that this blue distance is 16 theta. How we doing? Everybody happy? Okay. So thus, position of the axle as a function of theta is that simple little formula. Okay, next, let's talk about this difference vector. So the difference vector here that we were talking about, right? That vector. We know that this magnitude is 8. And this vector is going to start going around in a circle. So it's tempting to say, well, hey, cosine theta, sine theta. Right? But notice it's not going counterclockwise like if you say cosine theta, sine theta, that goes counterclockwise. And this tire is moving to the right, it means it's rotating clockwise. So, okay, that's a little different. Easy variation though, and specifically notice that going counterclockwise versus clockwise, these two different rotations give you the same x-coordinate as a function of time, theta, as a function of theta, but they give you negative y-coordinates as a function of theta. So all I'm going to do is I'm going to take this familiar red parameterization, cosine theta, sine theta, and I'm just going to put a minus sign on the vertical, on the second coordinate. And that gives me this. Here we go. Right, the magnitude was 8 because it's halfway down the tire, so it's got a magnitude of 8. Radius was 16. Cosine theta, sine theta, minus sign on the second coordinate to recognize that it's going clockwise. And so we're done at this point. So here is it all added together. The A vector is these terms right here. That purple difference vector gives you those terms right there, and all we've got then is that our reflector is located at both blue plus purple, picture we previously drew, and here's how those add up. So not that big of a deal to parameterize, but again, kind of a devil to figure out, what is this a graph of? And you can kind of see it coming, right? I mean, look at these expressions here. We've got sine and cosine, but we also have a theta in here, and we've got this constant of 16 just sitting there being annoying. What algebraic relationship can you immediately see between these? I think it's going to be quite tricky. Off the top of my head, know how to do that. So what this is a graph of, really hard. How to parameterize, no big. Okay, so the big moral of this story is not how to understand bicycles. The big moral of this story is how to understand vectors and how we used, vector addition and vector algebra to be able to parameterize something pretty non-trivial. Okay. Alrighty. Again, more examples. I encourage you to take a look at these. Lots of different sort of, it's all examples of stuff that we've already seen examples of elsewhere. Okay, so we move on now to limits and continuity. There's a lot to say about limits. We're not going to do all of it. I am going to kind of skip some of these things. I want to remind you about single variable limits. Some of you all have probably seen the epsilon delta definition of a limit before. Here it is. Just by the way, maybe a quick historical note. This was the conclusion, you might say, of a centuries-long debate in math. It started off with, when calculus was first being developed, with this idea of, what do you mean, take a limit? You mean you want this value, y'all remember in the definition of a derivative, you let h approach 0? Right? And you say the limit as h approaches 0. And the idea is, well, we want to, so h is going to be so small that it's effectively 0. Now, importantly, it's not 0, but it's like it's 0. We're going to pretend sometimes that it's 0, but in other circumstances, we're going to be very emphatic about the fact that it's not 0, because you can't divide 0 by 0. So it's sometimes 0, sometimes not 0 is what it kind of sounded like. That's a problem, right? Philosophically, this is not sturdy, right? And some people wanted to develop an idea called infinitesimals, which is a made-up concept, right? And also, you can debate, is this a real thing or is this a bunch of made-up nonsense? And if it's a bunch of made-up nonsense, then can we really believe anything that comes out of it? Well, calculus gave some very nice results that were clearly accurate, and it was clearly putting out good stuff. And the question of formality, arguably, as to figure out what is the definition of a limit on which we base ideas like derivative and ideas like integral. By the way, how's that for important? Limits are a necessary part of the definitions of both derivatives and integrals. All of calculus rests on what is a limit. And it was shaky. Right? So it was a pretty big something to worry about. Eventually they started to work it out and figure out a reasonable way to define a limit without doing a bunch of hand waving and making reference to nonsensical things. And this is what they eventually came up with. And this was, by the way, this was 150 years after calculus first, got conceived of. So it was a long time. This was a very hard definition to come up with. And so as such, it's a big deal. But it's a little hard to parse through. The big idea of the definition is, we would like to say, I guess I'll zoom in one bump here, let's give myself more space. If I would like to be able to say that, at this value A, that the limit is L, what I mean by that is that no matter how small I make this interval around my alleged limit L, no matter how small that is, no matter how tightly I require that the function be near that L, that I can make that happen. That I can accomplish that as a goal simply by requiring x to be somewhere. Well, I need to, let me use a pencil. Simply by requiring that x be somewhere in this interval here. And you'll notice I drew a little circle around A itself, where the whole point of a limit is to be able to talk about something that the function is doing, even though it may be undefined at A. So very important that you don't want, if your tool is to avoid A, you don't want your tool to involve requiring looking at A. So we're never responsible for what the function is doing at A. But no matter how close I need the function to otherwise be to my alleged limit, I need for there to be some constraint that I can put on being near A, so that no matter which value of x I pick in here, I need the values to always land in that value L. So it's a hard thing to talk about. It's students always want to talk about it backwards. Students always want to say, as you get closer in the domain, as you get closer in the input, that the output values get closer in the output, and you really can't make that work. The thing that makes this definition work is the going sort of seemingly backwards of starting with, let's first talk about how close we need to get, then see what constraints on x will accomplish that, and then we can say that we have a limit if, no matter how small that is, if there's always a way to make it work. All right. Okay, so we're not going to go in any more detail into that. I will point out that in that picture, we can draw it a little differently. Here's a different way that I could draw. Remember, not everything is a graph. You don't have to think about everything from the point of view of graphs. But let's draw that same picture. Here's our function f, about which I would like to assert that as I approach A, I would like to suggest that the limit is L. And the way I make that happen is to require that no matter how small that interval around L is, that there must be some corresponding interval around A that makes that work. So same idea. Notice all I did is I just kind of separated the x-axis from the y-axis because who cares, right? We don't need to have a graph picture for this to make sense. And the reason I want to do this is because, as you know, while in single variable context, graphs are great, you can pretty much understand everything you need to know about single variable calculus from with the visual aid being graphs. As you also know, that is not the case in multivariable, right? And so I want to pull myself away from the graph picture so that when I do an analog of this picture, I need it to be something that I can actually draw, and I can make a multivariable version of this picture. It's really hard to make a multivariable version of the graph picture. So here it is. If I have a function f, if I have a function f from R2 to R1. So two-dimensional domain, one-dimensional target. And if I would like to say that as I approach some now point A, not a value, but I point A in the domain, if I would like to say that the limit is equal to this value L in the target, then what I need to show is that no matter how small of an interval I make around L, I need to show that there is slow down. I needed to, over here in the single variable version, I needed to look at an interval around A. What do you mean an interval? An interval doesn't really make sense if your domain is two-dimensional. right? So let's reconcile, because what is an interval? An interval is the collection of all numbers, the collection of all points that are within a certain distance from A. A radius, we're going to call that radius delta. So likewise, over here, the analog of this interval, the meaningfully natural analog of this picture in this context is to draw a disk around A. Yeah. So like that. So let's go through the definition again. In order to be able to say that as I approach A, the limit is L, what I need to show to make a definition is that no matter how small this purple interval gets, that there is some appropriately small yellow disk over here with the property that every point in this disk, other than A itself, remember responsible for A, every point in this disk has an image that lands in here. Said differently, no matter how close you require that I get to L, I can ensure that we get that close just by putting this constraint, this yellow disk constraint on how far I'm allowed to get from it. Okay. So anyway, that's the analog, and that's what motivates this definition here. This is the multivariable definition of a limit, and I just thought y'all should see what that multivariable definition of a limit is. Again, it's kind of a big deal, right? But it is hard to work with, and that is really arguably a point that is more appropriate for a higher level math class. So I'm not really going to do all that much with this definition as written here. Okay. All right. Okay, so in practice, how do we deal with this? By the way, I'm not going to prove a lot of the stuff that we're going to do, a lot of the assertions that I'm going to make about how you compute limits. I'm going to assert certain things, and run with them. Right? Because again, it's a much higher level math class to prove the results that I'm going to be using here. So one result I'm going to use is that if you need to compute a multivariable limit, if you are approaching the origin, and this is peculiar to this one, it's got to be limit as you approach the origin. Then one way you can rewrite that, one way you can compute that, is to just rewrite it in polar coordinates, specifically rewriting in polar coordinates with just r approaching 0. It's kind of a reasonable observation if you think about it. If a point in the plane is approaching the origin, it's approaching, it doesn't really matter if it could be approaching in a spiral, or it could be approaching with a kind of a zigzag pattern, but if it is approaching, getting arbitrarily close, right? And if it is approaching the origin, r has to be approaching 0. Yeah. And furthermore, if a point is doing anything that has r approaching 0, it can wiggle around all it wants in the theta direction, but if r is approaching 0, the point has to be approaching the origin. So I think it's a pretty easy appeal that these two kinds of limits really do say the same thing. That's not a rigorous argument, of course, but this is, I think, highly believable. So the neat punchline is we notice that we have gotten rid of a multivariable limit, and we've rewritten it as a single variable limit. And that's something we know how to work with. So here's an example. Let's try to compute this limit here. Note multivariable limit. Two different variables, x and y. X and y in the multivariable sense are approaching the origin. What do we do? How do I compute this limit? And the move is to use this trick. We're going to rewrite this in polar coordinates. Notice x is r cosine theta, and y is r sine theta. And if you plug that into here, notice we have, let's see here, x cubed y squared over x squared plus y squared. So here we go. x cubed y squared over x squared plus y squared. That's just a recopy of the function, but writing it in polar coordinates. Rewriting the multivariable limit as r approaches 0. And we've rewritten the limit now as a single variable limit like this. Now, this is something to worry about. We're not done yet. Let's think about what we got here. Take stock. We have a limit as r approaches 0. I see that there's an r cubed here. That's nice. That r is the same as this r, so it's looking good so far. But then there's all this theta business. Right? Now, per my argument before, if you're approaching the origin, and if you're governing that approach of the origin simply by requiring r approaching 0, notice theta could be doing all kinds of... We have no control over theta. Theta could be going to infinity. Theta could be constant, right? It could be zigzagging. I've got to slide it. We have no control whatsoever over theta. The reasonable worry, how can I possibly compute a limit if I only know what one of the variables is doing? R is approaching 0, but theta is going crazy. How can I know what's about to happen here? And very often, you don't know. That is a problem. It is something we have to worry about. But in this case, it's not a problem. And here's why. You will get lucky sometimes in this way, and that is, let me zoom in for... If only my eyes are getting old. I have a product here, right? And sure, I have no awareness of what theta is doing. Theta is going crazy. I have no control over this factor, except for the fact that this is cosine and sine, which are bounded. And I don't really care how crazy theta is in a box, right? It can bounce around as crazy as it wants in that box, but cosine cubed times sine squared will never get out of the box. That's always between -1 and 1. This is bounded. Yeah? And r cubed is unambiguously going to 0, right? So what we have here is something bounded, uncontrolled, but bounded, multiplied by something that's approaching 0. And that's not a hard question, right? Something approaching 0, something that's bounded, it's not a fair fight that this limit is 0. Everybody happy with that? Okay. Now I emphasize, you'd better make sure, if you want to apply this argument, you'd better make sure that this thing that's being multiplied by something approaching 0, you'd better make sure that thing actually is bounded. Right? If this were, hypothetically, different example, if this were r cubed times theta, well, theta, that's not bounded. Theta could be going crazy. You could be going to infinity. I don't know. Right? And then your argument crashes and burns and you don't have an argument. Okay, so careful with that. All right. Let's see here. Okay. Where's my... Here it is. Okay. So here is a mistaken impression. Let's go back to single variable limits for a second. Let's look at this picture because it's analogous. So y'all may recall that one way you can understand limits is by, on the one hand, looking at what we call a left-hand limit. Let's look at, what happens if we approach A from the left, and then look at what happens as we approach A from the right. That's called a right-hand limit. And you can entirely understand a limit by the left-hand limit and the right-hand limit. If these left-hand and right-hand limits, if they both exist, and if they equal each other, then that value, that shared value, is the limit. Okay, so you might think, right, you could totally be forgiven for presuming that that would have an analog in the multivariable case, and namely that, wouldn't it seem to stand, wouldn't it seem expected that, if you can understand what happens as you approach A, let's say along that line, as you approach A along that line and that line and that line. If you can understand what happens as you approach A from all of these lines, if along all of these lines you always get the same value, L, surely the limit would have to exist and the limit would have to be L. Doesn't that seem likely? And of course you can tell from my tone that I'm building up to a yeah, but. This is actually false. This is not what a multivariable limit is. A multivariable limit is weirder than this. It is not good enough to simply understand as you approach along all straight lines. This is going to seem super stupid, but approaching along all these straight lines does not necessarily tell you what happens as you approach along a curve. And it seems, right? Who cares who cares if it's curvy over here, right? All that matters is what's happening as I get down to business and start and really get close to the point. And as you're approaching that point along this spirally purple curve, near the origin, it is kind of straight there. And come on, it's morally just like one of these lines. And what's the difference? Right? And believe it or not, there are examples of functions. I'm going to show you one in just a moment. There are examples of functions where if you approach along all different blue straight lines, all of them, always get the same value. And yet if you approach along a purple curve like this, you get a different value. And I don't know what to tell you other than multivariable functions are they're weirder in a way that single variable functions don't demonstrate. There's a whole extra level of weird. There is no single variable analog of this. It's just super weird. Okay, so this leaves us in a difficult circumstance where, again, we can't just look along all straight lines. Let me show you. This is a good example. I'll do this one. So let's look at this function here. Not that weird of a function, really, at a glance. You give me a point x. By the way, notice this is not defined at the origin. And I'm going to define the value of my function to be the magnitude of x, that's a simple idea, divided by the angle, theta, of that point x. And the only little detail I have to point out here is that theta, I can't let theta be 0, that messes it up. So if you're on the positive part of the x-axis, just don't choose theta equals 0, choose theta equal to 2 pi. So for every point in the plane other than the origin, we're going to theta will always be between 0 and 2 pi, just pick 2 pi instead of 0. Okay, so the function's not that weird, right? It's magnitude, so distance divided by angle. All right, well, let's look along straight lines. Back up to this picture. I'm going to parameterize this straight line here. That's a straight line that I'm going to say approaches the origin. I'm going to do that by noting that if I have a unit vector here, u, then a multiple t times u gives me a point like that. And if I just say, let's look at tu, or if my base point is a plus tu, let t approach 0. As t approaches 0, we approach our base point. So that's all I'm going to do down here. Let's look at 0 plus tu. I'm going to let t approach 0. Of course, this is tu. F is magnitude divided by angle. And let's think about this thing that we're looking at here now. I'll zoom so I can point. What happens as t approaches 0 to the magnitude of TU. Well, T is approaching 0. This vector is getting shorter and shorter and shorter. This distance is approaching 0. What's happening to this angle as T approaches 0? Well, as T approaches 0, we're getting closer to the origin, but we're staying along that same line. The angle's not changing at all. So this denominator is constant. I don't know which constant it is, but it's somewhere between 0 and 2 pi. Who really cares? It's constant. The numerator is approaching 0. This limit is clearly 0. Okay, so this calculation here, notice this applies for all unit vectors. This means that what we've done here is we have effectively checked along all possible straight lines, all of them. Along all possible straight lines, this limit along those straight lines is always 0. We feel this overwhelming urge to say, and therefore this limit's got to be 0. But it's not. Check out, where did it go? I'm too zoomed in. I can't see what I've got here. Yeah. Check out I need to do this in purple. Check out this curve. Magnitude of x equals theta. Let me draw a picture of that. This says that as theta increases, my distance from the origin increases. This is a spiral. Right? As theta increases, my distance from the origin increases. That's a curve. What happens as I approach along this curve? Well, along this curve, magnitude always equals theta. Along this curve, magnitude always equals theta. That means that this function is just flat 1 everywhere along this curve. Now, what is the limit as you move along a curve? If the function that you're taking the limit of, if that function is constant as you move, the limit is that constant. Along this purple curve, the limit is 1. So along the blue curves, the limit was 0. Along the purple curve, the limit's 1. That ain't right. Wouldn't be reasonable to say this limit's 0. Doesn't make any sense. Everybody on board? So this is what we have here. Mysterious though it is, what we have is like an example. The single variable analog kind of this would be a single variable limit or a single variable function where from one direction the limit was that value, but from a different direction the limit was that value. We have some sort of a jump discontinuity here. Now, exactly what this function looks like, what is the graph of this thing? How could this be? That's a harder thing. I can't do it with my hands. With a visual aid and some time, I could show you a picture of what this thing looks like. But punchline is, it clearly has a very nasty sort of a discontinuity in it, and there's no way that it can be fixed. Everybody on board? Yes.
Is there a geometric interpretation of the function we define?
Yeah, that's what I was saying. It's kind of hard. I can manufacture a picture, but it takes a little bit of time and some doing and a visual aid that I don't have on me. So it's a weird function. Let's just say it like that. And we're going to see more examples, by the way, of weird oddball functions kind of like this. Yeah. Okay. So here's the lesson. The lesson from this is, where did it go? Well, here it is. If you want to understand a multivariable limit, and if you want to understand that with single variable limits, and by the way, we really want to understand multivariable limits with single variable limits because we know how to compute single variable limits. We took classes in single variable limits, right? We're good at that. You have to consider not just straight lines. You have to consider all possible continuous paths that approach your base point. Got to consider all of them. Side note: you can't do that. There's too many. Right? There's a staggeringly infinite number of different curves. You just can't check all. There's temptation to say, "Well, I'll check all the lines." What comes after lines? Parabolas, cubics, spirals. Is that enough? Nope. You got to check the quartics and the quintics and then even after that, now we have to consider all the little zigzaggy things. And then what about something that's zigzaggy, but in a kind of like a spirally way? And oh my gosh, you can't possibly enumerate all possible paths. So the only way that this is actually useful is by turning it around backwards. And so if you find, for example, two paths along which you get different limits. Oh, well, if you find two paths with different limits, well then clearly all paths can't give you the same limit, because here's a counterexample, and therefore you know the limit doesn't exist. All right. So this business about checking along paths can prove that a limit does not exist if you find such a contradiction. But no matter how many individual curves you check, no matter how impressive your list of checked curves might grow to be, it's never enough. And you can never use this to prove that limits do exist. Okay, we're out of time, so we will pick up here with some examples. See, what's today? Is today Friday? Okay, so we'll pick up on Monday with this. Okay, see y'all later. Oh, see y'all in a few minutes, because we're about to go get some lunch.